All right, so we've kind of done this like conceptual stuff. Let's go in and do, because it's internal flow and we care about how the flow develops and changes as you flow along the pipe in a maybe thermal setting or shear stress setting, we probably want to do some kind of a formal analysis around this, like we've done with other things. Let's go here. So next page, what we're going to do is, let's do a momentum balance on this so that we can look at how we'd model like pressure drop and things like that. So we are focusing on the momentum side of it for now, but a lot of the same concepts obviously apply to the thermal side. This being a heat transfer course, that's where we're going to go with it. But for now, let's just stick with this. So we have our pipe. We have flow going this direction in it. And so what I want to do is maybe draw like a control volume. So I'm going to draw a control volume where I look at the momentum considerations. I'm not going to do this as like a 2D model. Let's just do it as a 1D model in the flow direction. And what we're trying to do is look at the conservation set of momentums. So let's say we want to look at the sum of forces in the x direction plus x momentum in. That has to equal x momentum out, plus if there's any time rate of change of x momentum internally. For this problem, let's assume it's a steady flow problem. Like you have this, flow is moving, but it's sort of a steady, not changing with time problem. So let's go ahead and throw this last term out, and then maybe do an inventory of the other stuff. So on this control volume, for momentum coming in, let's see, we have in here would be momentum. So momentum is going to be rho times u squared, where u is our velocity profile in y. Right? So this is our y coordinate. This is x coordinate. So u is a function of y. But we need to look at, because it's changing, we want to look at the full momentum over the entire height. So we have to do an integral. So that's going to be the area integral. So A sub c, the cross-sectional area, d A sub c. And we're evaluating all of that at position x. And then leaving, we have something similar. It would be the area integral AC rho u squared dAc at x plus dx. We also have pressure. You know that the pressure is changing as a function of position here. So pressure would be P times AC at x. And then leaving, we would have, let's draw it. Usually draw pressures both going in. So on the other side, it would be PAC at x plus dx. So pressure here, pressure here. What else are we missing? So we said there's no change in time. We also have shear force on the upper and lower edge. So let's introduce shear force. So up here would be in this direction. Call this tau s. And instead of saying we've got like tau s on the top and on the bottom, let's just say we don't actually know what the geometry is. We'll just describe it in terms of a perimeter. So tau s times the perimeter times the, we're looking for the full area. So this, I guess, is dx, right? Dx times the perimeter. Tau s perimeter dx. This distance here, dx. Okay, so that's our control volume. Let's go through and write this out and get to the point where we can do analysis with it. So, okay, just writing it out down here. Pressure AC at x minus tau s perimeter dx minus pressure AC at x plus dx. So this, by the way, these terms here are all forces in x. Plus, what else is happening here? We have plus the area integral AC of rho u squared dAc at x. And then I'm going to jump down here to save some room. So that's all equal to, on the right-hand side, the area integral rho u squared dAc at x plus dx. So we have our forces in x. We have x momentum out, and we have x momentum in. Or vice versa, what did I say? X momentum in, x momentum out. OK, so going a little further, I guess we can cross some stuff out, right? We have, how do I write? I better write it out. So I'm just going to write this out, try to save some room here. So PAC at x minus tau s perimeter dx minus, now let's expand out the pressure term. So the pressure term expanded out is PAC at x minus d PAC dx times dx plus area integral, so this is AC, rho u squared dAc at x is equal to, so that's the left-hand side, then that's equal to, expanding out the momentum would be AC rho u squared dAc at x plus d dx of that, AC rho u squared dAc at x times dx. Let's see, what else? Did I miss anything here? So yeah, I think that's it. So let's cancel stuff out. So we have the pressure term here. That part goes away. Let's see, we have a positive x here and a negative 1 here. Oh, sorry, that's not it. This one here. This one here. Did I get them? I think that's it, right? So we're left with a differential here. Once we canceled those terms out, we have tau s perimeter dx, something dx, something dx. So dx can go away as well, which is good because we never want to carry around dx's. Dx goes away. And then we're left with this kind of simplified equation. So that's just minus d PAC dx is equal to tau s times perimeter plus d dx of AC rho u squared dAc. Turns out you can actually write this slightly differently. So the last bit here, we can write this equivalently as 1 over AC times the area integral AC rho u squared dA. So there's a very slight difference there, but it helps us then do the area average integral. So okay, so we get to this point. Now we have like a differential equation. We're out of time, but what I'll say before I wrap up here is let's just take a second to look at what this is telling us. So this is telling us that there's a relationship between the pressure gradient in x internally, shear stress, and momentum, right? Which makes sense. So what we're going to do next time is continue going through this, but we'll come up with ways to then like conceptualize when is this part important, when is this part important, and how do we use it to calculate dp dx.